Okay, I'll start with giving some description. There is some collaboration work done around DDC. A lot of the work that we are going to present here was done by AT&T, led by Shiva Kumar Mysore, and he was not able to attend. Some reasons to do with AT&T and how they travel, but nobody could actually attend. So that's us, Drivenets, and Ufispace. We're going to pitch this to you guys today. Kai from Ufispace and myself are going to kind of switch places in this introduction. Now, you're going to try to fix it?
Can you power down?
The presentation or the laptop?
The laptop.
No, let's not do that. It will take 10 minutes.
The first slide is about introduction of while they're trying to fix it.
What do you want me to do?
It's about introduction of DDC, Disaggregated Distributed Chassis. And this definition came from AT&T since 3-4 years back and was made as a contribution to OCP. Now we're talking about DDC version 2 in this session. So let's try to understand what is version 1 before we jump into version 2. DDC is essentially a chassis which is running an application called routing. So all of you are probably familiar with the term router. What we did is we took every component of this router and we built it as a standalone entity. So the line card of the router is now a standalone box. We call it NCP or DCP in OCP terminology. The fabric devices or the fabric cards of the chassis is now called NCF. Right? There is also a routing engine which is run on a server or on the cloud, on something that runs on an x86. Let's put it this way. You call it NCC. Or DCC in OCP terminology. And there is also a management plane, in which case we're using a standalone switch, which is also an OCP design, but that's just something that we took off the shelf. So the server is off the shelf, the network management switch is off the shelf, and then there are these two new devices, which essentially are the line card and the fabric. The same way as you would connect a chassis, you would connect the line card to all the fabric elements. That's what you will have in a DDC. You can see the formation here. It's kind of a simple class topology. And every such device can act as a standalone. There's a CPU on it, and it runs as a standalone device. If you take it out of this array, this class topology, it will act as a standalone device. You can do whatever you want with it. You can run it as a router. It's a functional machine. When you build all of this into a unified cluster, this is mainly where the DDC comes into play. The Drivenets software takes all of these components, all of these elements, and the Drivenets software, what we call DNOS, Drivenets Network Operating System, runs on all of the components at once. So the way that we build the software is as something which is cloud native, so it's distributed. It runs on multiple machines as one unified entity. So we have containers which are holding a subset of the network operating system, the NOS, and this container, or the relevant container is run on each of the devices. And eventually, there is a controller which groups all of this together and makes the entire cluster work as one unified entity. Now, I'm calling it one unified entity and not one router because there is a difference. It's not just running routing. Routing is the first function that we enabled. This is what's running the core network for AT&T. Core router that was built exactly like this, right? But it can also be true that an additional router can run on that same infrastructure. So the coexistence of multiple routers on the same infrastructure, on that same cluster, is a possibility. And there is also a possibility of running a different network function, which is not routing. So you can essentially run a firewall, a load balancer, a DPI, a DDoS mechanism, as network functions. And when you kind of extrapolate this a little bit onwards, then these applications can be practically anything. Keep in mind that we have NPU, lots of these NPUs as resources. We have lots of CPU as resources, and we have a hypervisor that orchestrates all of this and then enables all of this available hardware to whatever type of an application that we have. This is DDC, right? So we're going to look into DDC. What is V1, V2? Kai is going to take you through what's upcoming as part of DDC V2.
Thank you. So I'm Kylie with Ufispace, locally here in San Jose. Our company headquartered in Taiwan, and we focus on building white boxes based on merchant silicon. So about 3 years ago, we had the opportunity to come to OCP jointly with AT&T. We talk about the DDC Fast Forward. Now we are talking about the version 2 today. So a couple of things, as Rand was talking about, DDC, Distributed Disaggregated Chassis. Basically, we are taking a traditional chassis, break it down functionally, and build this into pizza boxes. The route processor, the switching fabric, the line card, 100 gig, 400 gig, or whatnot, we break it down into pizza boxes. Now, why are we doing that? Number one is fun. Number two is for scalability. You scale this horizontally. You don't get into a gigantic chassis with one line card and a big power supply drawing all the power. So DDC is mainly for scalability, pay as you go. V1, we did it 2-3 years ago here at OCP, along with our customer AT&T, going into production already. V2, what we are bringing today is an additional member. On V1 is mainly the switching fabric using the merchant silicon from Broadcom, the Ramon chipset, and also the Jericho 2. With the Jericho 2 building the line card, at the time we have the 100 gig line card and the 400 gig line card. Fast forward, we introduced V2 on a couple new members, namely the more advanced version of the J2 chipset called the J2C+. The J2 is at 4.8 terabit per second switching capacity. J2C Plus is 7.2. We use a dual chip design, and basically the new box was born that we can bring up in the same 2RU box with up to 36 gig of 36 port of 400 gig QFSPDD connection in a non-blocking. Additionally, we also have a baby version. If you are familiar with the Broadcom DNX kind of their family naming convention, we started with the J2 in the middle. J2C Plus is the big brother from 4.8 to 7.2 terabit. Then there's a baby version called the J2C. That is half of the J2 at 2.4. So another member we are showing today is the J2C at 2.4. That one is focusing on 25 gig connection, downlink to your server farm. We can break it down to 1 gig and also 10 gig. So that's a quick summary of the V2. And here's a specification that we want to include. When you download the slide, you can see all the different specs of coming in from that. As Rand was talking about, the DDC Distributed Disaggregated Chassis, we broke it down by function, the route processing, the line card, the switching fabric, and also the management switches. So some of these things are basically come together to make up the cluster, both from a functional and management perspective. This is the new one that we are introducing this year. It's based on the J2C+, 7.2 terabit per second. We have a dual chip design. Optionally, we can get the OP2 or the knowledge-based processor for external TCAM caching. If you have a gigantic BGP table or a lot of ACL, we can do the content adjustable lookup. We use 2 chips. The 2 chip, if you believe the math we all did together along with our hardware team, came out to be 36 port, maximum 48, 400 gig in a non-blocking architecture. Everything we build for telco, we try to do non-blocking. It's very important we do that. So that's the big brother. And just for the reference, we also include a block diagram. You see the dual J2C. Then we have the control plane with the Intel processor, and then we have a few other things on this block diagram. Then we have the baby version, which is a J2C. This is at 2.4 terabit per second. This one focuses on 25 gig high-density connection, 64 port with some 100 gig uplink and all that. The use case for this is downlink to the server farm. Before this box was born, with the traditional J2, we have a 100 gig port. And what the customer had to do is to buy a breakout cable to break out a 100 gig port to either 425 gig or 410 gig. Because the way how the SerDiff is designed, if you break it down to 10 gig from 100 gig, you don't get 10, you get 4. It's just because of the number of SerDiff is available on the chip. This solved the problem. We are using the chip a lot more effectively. Starting with 25, you can break it down to 10 or 1. You don't break it down from 100. So this is a more economical solution for those that you need downlink for the server farm. And similarly, we also provide the block diagram that you can take a look at it when you download the slide. So backward compatibility, we build this based on the same space. When you talk about central office data center cooling space and heat dissipation, We consider all this, so we want to make sure the form factor, the 2RU, and all these other things, you have pre-existing power and cable wiring. So we want to make sure the new member on the version 2 goes into your rack from an installation and deployment perspective in a very easy way. So with that, I'll turn this back to Ram to talk about the DDC firmware.
Thank you, Kai. This will not take too long. What we did as part of V2, it's not just additional boxes. Additional boxes are being added all the time. Ufi is very generous in contributing all these things and making continuous development here. As new ASIC, as new requirements come in, more devices with more variety, and they all can punch into that same DDC cluster, the same original cluster, because it's the same fabric technology that connects them all. What we did in this case, keep in mind that when we took a chassis and we broke it into its pieces, and then we created a problem that connecting all of these back is a challenge, right? And that challenge had to do a lot with synchronizing all the devices, and of course we solved all of this. And then we got to the point of saying, all right, there is an issue here which is still not fully resolved, and that's the issue of upgrade. When you try to upgrade a system, then it's one component. When you try to upgrade a distributed system, now you have multiple components, and there is synchronization in between. This is where that firmware upgrade mechanism comes into play. Now, the ecosystem is wider. It's not just Drivenets as the software, which is an option. You can find alternative software. I'm not going to tell you from where, but it's there. And then you can find additional boxes, not just Ufispaces. I'm not going to tell you from where. But they are there, right? Everything, the interconnect, everything is dual source or even multiple source. You can get this from multiple places. The thing is that eventually you will need to get, as a user, you will need to get upgrades. And sometimes this upgrade is not necessarily for the software, but also from the firmware. So in order to create decoupling from getting updates on the firmware and the software, so not to have the Drivenets software as kind of a proxy or a block, for you to update your system, you need to update every component as a standalone. And you can do that manually, log into the box, and just create kind of a firmware update. It's very cumbersome. You need to do that multiple times because you could have 50 or 100 boxes per one cluster. And if you make a mistake, you're dead in the water. Right? So this is why we needed a mechanism to kind of control all of this together and still protect the user from doing any form of mistake. In order to do that, we needed to create a standard. And that's exactly what we did. We created a standard that communicates between the boxes and the software. Right? There is a tarball file. There is a JSON format that is being produced by the ODMs and communicated to the network operating system. And then the network operating system takes care of two things. One is that everything to do with the order of the upgrade is going to be kept intact. Upgrading the NCF before you're upgrading, the DCF before you're upgrading the DCPs. Why? So you will not have a case where a leaf, like a DCP, will remain kind of stranded, not being able to connect to the NCF because it's running a more refreshed software or firmware, which is not compatible. So the level of compatibility needs to be controlled. So DCF, DCP, DCC, DCM, all of the components, they have an order. Right? So making sure that this entire process is intact and happens properly is the responsibility of the software. That's the first item that we try to solve, and we solved. The second item is getting an indication. When you're a user and you upgrade a cluster, and there are 200 components in this cluster, this is a process that can take a couple of hours. Right? And if this is the case, you want to know where are you in this process, not just as a whole, like I upgraded DCP number 1 or number 5 or number 6. What's the process within the DCP? Within that single device which is currently being upgraded, where am I in this process? So we added these indicators as well so that the user have a very clear indication as to where he is in the process. And if there is failure, then the software will roll back per component. Right? Not for the whole cluster, obviously. So if you have any kind of a hiccup in the process, and these hiccups do happen, I think that everybody that ever upgraded a network device knows that these issues do happen. This is the second problem that we try to solve, is to take care of the fact that the user eventually will have a full clarity on what's going on. All right, these are the two things that we try to solve, and it's part of the V2 of DDC. Now, as a call to action, DDC is a live and breeding protocol or standard. There isn't a V3 in place, but there are some items that we're working on. There are security aspects. As I said before, there are additional devices which are coming into play, additional functionality which is being added, additional use cases which are being added to this type of an implementation. There are multiple teams who are contributing. Specifically this spec had contributions coming from Delta, DNI, EdgeCore, Ufispace, obviously, ourselves, and AT&T. And we're calling everybody in the industry, to come to pitch into this. Software components, hardware components, even interconnect components can have an active role in this. And obviously, end customers. It's not tightly coupled to service provider space. We also have some engagements with customers here on the hyperscale arena. It's very active when it comes to AI, ML. You heard a lot about this this morning in various sessions. The model works, and it's basically boiling down to the capacity of the silicon, but you do need some software to make all of this work, and you do need boxes that are built to last. That's it from our end. If there are any questions, we'll be happy to take them.
Thank you.
All right, thanks. Thanks, guys.